Europe, one of Jupiter's moons, is covered by a thick ice crust, and beneath that ice, there might be a true ocean of liquid water, one of the prime places to search for life in the solar system. However, outside of Earth, this feature is shared by many other places in our planetary system, such as Enceladus, Titan, Triton, or even Pluto. These are what we call ocean worlds, meaning those planetary bodies that could indeed have a liquid water ocean. But how can we be sure? How do we know, just by looking at them from the outside, that there is actually an ocean there, and if there is, could it harbor life? We will discuss this calmly in this video. Until the 1990s, our knowledge of the outer solar system was quite limited. In fact, we had only briefly studied Jupiter and Saturn with the Pioneer 10 and 11 probes and then the 4 giant planets with Voyager 1 and 2. These were quick flybys, overviews of these worlds, which offered us many insights but no in-depth knowledge of their systems. Despite having so little data available, an extraordinary hypothesis was formulated. Some of the icy moons of the giants could host liquid water oceans. After the disappointment of Mars, which appeared as an utterly inhospitable world for life through the Mariner and then Viking missions, the possibility that life could exist somewhere in the solar system was suddenly reignited. With the Pioneer and Voyager missions, these places acquired a face, even though the first theoretical studies on the possibility of subsurface oceans came even before these probes. For example, in 1971, a theoretical study published in Science by astronomer John Lewis demonstrated that radioactive decay inside the larger satellites could maintain a liquid water ocean by heating it and preventing it from freezing. This worked particularly well if ammonia was present alongside water, as ammonia lowers the freezing point of water, making it possible to have a liquid water ocean even at lower temperatures. And the outer solar system is full of ammonia. A few years later, when the Voyagers were flying by Jupiter in 1979, another study showed that tidal heating could play a role, for example concerning Europa, in keeping this ocean warm. We will look at these things calmly because they are very interesting. But the point is that theory and hypotheses told us that a subsurface ocean was possible. Between the 2 millennia, the Galileo probe explored Jupiter and its moon system, just as the Juno probe is doing today. The Cassini-Huygens mission did the same in Saturn's system, while other telescopes, both ground-based and space-based like Hubble and James Webb, have continued to study these moons from a distance, from Earth's environment. In short, today, 50 years after the Voyager flybys, we know these systems much better and have begun to gather clues that confirm, if you will, those hypotheses. We believe that at least some of these moons almost certainly have liquid water oceans. But how can we be sure that these oceans really exist? How do we gather data on something we cannot actually access? And above all, are all the oceans of icy moons really interesting from an astrobiological point of view? Before continuing, like the video, subscribe to the channel, and activate the bell to not miss the upcoming content. There are quite a few possible icy worlds in the solar system. However, it's worth noting that for most of them, we are very uncertain whether there is actually a subsurface ocean or not. Around Jupiter, there are Europa, Ganymede, and Callisto. Around Saturn, Titan and Enceladus. Around Neptune, there is Triton. And then there is also Pluto which, although not a satellite, could still have a liquid water ocean. Water might also be present in other places, like inside Ceres in the main belt, or in Ariel, a moon of Uranus, and many other icy satellites of Uranus, Neptune, Jupiter, and Saturn. In all 4 giant planets, it is often said that oceans can remain liquid thanks to tidal forces generated between the planet and the satellite, and this is certainly true but not the only factor at play. In general, we need mechanisms that can produce heat inside these icy bodies, thus warming the ocean and preventing it from freezing. One of these is undoubtedly tidal forces, the same ones we know very well here on Earth. When we see the sea level rising or falling, we have a body in orbit around another, and the mutual gravitational attraction is not the same at all points. It is stronger where the 2 bodies are closer. That is, if I am on the side of the Earth facing the Moon, at that moment the Moon's gravity pulls me stronger than if I were on the opposite side of our planet. The issue is more complex than that, but the basic point is this. So, if I am closer to the satellite, it pulls me more compared to when I am farther away. But this mechanism does not only occur for water. It happens for any material point that is in the direction of the satellite. So, even for the rock, there are so-called solid tides. The rock itself moves slightly towards the satellite, creating a tidal bulge, as it is called, in its direction. However, the forces act in both directions. So, if the Earth slightly bulges towards the Moon also slightly bulges towards the Earth. The same exact phenomenon happens for Jupiter's moons, even more so because Jupiter has a much larger mass. So, all the moons of all the planets are deformed, having a tidal bulge in the direction of the planet. The tidal bulge deforms the moons, producing internal stress, which means heat. Ultimately, internal friction is created among the particles composing the moons, producing energy that heats the oceans from within. But this is not the whole story, because the main mechanism by which these moons are heated internally is radioactive decay. Atoms like uranium, potassium, and thorium, contained within the nuclei of these icy moons, can produce heat when they decay because decay produces energy we see in the form of heat. This is the main reason why even planets like Earth continuously produce heat from their interiors. But there is also another reason that dates back to the origin of the solar system. All planetary bodies were produced by accretion, accumulating mass from the nebula from which the solar system formed. This accretion, which was very chaotic, produced heat that remained trapped in the hearts of the planets, continuing to heat them from within, even today. These three mechanisms are responsible for the heating of subsurface oceans, allowing them to remain liquid under the icy crust. For Europa, for example, tidal forces are particularly significant. Jupiter, with its enormous mass, exerts a powerful gravitational pull on Europa, which is further amplified by gravitational interactions with the other Galilean moons, such as Io and Ganymede. This constant tugging and pulling deforms the Moon and generates internal heat, keeping the subsurface ocean liquid. Evidence supporting an ocean beneath Europa's surface includes the ice surface with very few craters, suggesting continuous surface renewal due to geological activity. Additionally, the fractures and streaks on the ice surface could be caused by the movement of water beneath the crust. Enceladus, another icy moon, this time around Saturn, has become one of the most interesting places to explore thanks to its spectacular geyser eruptions. The Cassini probe discovered these geysers that spray particles of ice and water vapor into space from fissures near Enceladus' south pole. By analyzing data collected during close flybys, scientists found evidence of salty water, organic compounds, and silica, suggesting that subsurface water is in contact with rock, a process that could provide chemical energy to sustain microbial life. Titan, Saturn's largest moon, has a very different but equally intriguing landscape. Beneath its dense atmosphere rich in methane and nitrogen, there is likely an ocean of water mixed with ammonia. Additionally, the lakes and seas of liquid methane on the surface represent a unique environment that could host life forms very different from those on Earth. As for Triton, Neptune's moon, and Pluto, the data are less detailed, but there are indications of possible subsurface oceans there as well. Triton, with its active geology and nitrogen geysers, suggests a warm interior. Pluto, studied by the New Horizons mission, shows signs of possible recent geological activity, such as exposed water ice on the surface, which could be linked to a subsurface ocean. In summary, the ocean worlds of the solar system represent some of the most fascinating frontiers for the search for extraterrestrial life. Future space missions, such as NASA's Europa Clipper mission and ESA's JUICE, Jupiter Icy Moons Explorer, mission, will be crucial in gathering more detailed data about these moons. By analyzing the composition, structure, and dynamics of these subsurface oceans, scientists hope to find answers to one of humanity's oldest questions: are we alone in the universe? Thank you for watching the video. If you enjoyed it, don't forget to like, subscribe to the channel, and activate the bell to not miss the upcoming content. If you have questions or want to suggest new topics, leave a comment below. See you next time.